I'm starting the recording late, but all you missed was pressure conversion. So, sorry.
It's okay.
Okay. So that brings us to Boyle's law, the first gas law that y'all learned back in Chem 1. Robert Boyle was considered to be the father of chemistry. He was an Irish chemist, blah, blah, blah. You can read all that. I'm not going to read to you. Let's get to the meat of this, and that is, what is Boyle's law? And that is pressure and volume. P1V1 is equal to P2V2. And pressure and volume are what kind of proportional?
Direct.
No. Indirect, yeah. They're the only ones that are indirectly proportional. If one goes up, the other one goes down. Think of a gas in a piston. And if I increase the pressure to lower the piston, what does that do to my volume? I increase pressure, but it decreased my volume. So they are inversely proportional. Okay? Inversely proportional. Boyle's law has been tested over 3 centuries, which is a long time, and it holds true at only low pressures. Okay?
Is there a certain limit?
No. But here's a graph of pressure and volume, and you can see that is indirectly proportional. And here we go. So work that out. We have this particular problem. I'm only going to work one Boyle's law problem because I assume you remember it. P1V1 is equal to P2V2. Wants to know the new volume, so I'm going to be solving for V2. So it's going to be P1V1 over P2. So plug in the stuff. Pressure 1 is 5.6 times 10 to the 3rd pascals. My volume was 1.53. And I changed my pressure to 1.5 times 10 to the 4th pascals. Did I need to change this to atmosphere? No, because they're going to cancel each other out. If you're using Boyle's law or one of the basic gas laws, you don't have to change your pressures. If you're using Pivner, the ideal gas law, you want to change your pressures. Cancels, cancels, and we do that math, and we get 0.57 liters. Yes, Daniel, you have a question?
Isn't this the same setup as the dilution?
It is. It's just they happen to equal different things.
What was the dilution formula?
M1V1 equals M2V2.
Okay.
Yeah. Yeah. But the reason is because they're no matter what, pressure and volume are indirectly proportional. So if I increase the pressure, I have to decrease the volume. So that's why, just like if I increase the volume, I have to decrease the pressure. Okay. So that's why they're equal to a constant. Okay. And then that's all you do here. Okay. That should ring a bell, hopefully, from Chem 1. Okay. Okay. Ideal gases, remember, don't really exist. Okay. An ideal gas is, they don't lose their energy when they collide particles. They have no volume. Different components of that. You can approach ideal gas behavior, but it's actually like if the world was perfect and smelled like chocolate, there's these ideal gases. We can approach it. We can approach the world to being perfect, but there's there's conditions at which ideal gases will approach ideal gas behavior. Real gases approach their ideal behavior. And that is what? Do you remember?
STP.
No, not at STP. That's a good guess, though. Doesn't anything. No. So let's think about this conceptually. If I want a gas to approach ideal gas behavior, where should the particles be in relationship to each other?
Close.
Far, far apart. Far, far apart. So low pressures, high temperatures are going to be your ideal gas behaviors where they approach it. Because at low pressures, my particles can be very far apart. And at high temperatures, what are they doing? Moving around very fast, which means they can move even further away from each other. And then also non-polar compounds can approach it because in non-polar, there's not an interaction as much with the particles. Whereas a polar gas, the positives and the negatives of the poles are kind of attracted to each other. So low pressures, high temperatures, you approach ideal gas behavior, and non-polar have more of that. Okay? So that's the ideal gas. Okay? The good...
Ms. Parker, can I interrupt you?
Yes, let me pause the video if you don't mind.
Pause the video.
All right, resuming. All right, so this... we're not going to do this. You can do it on your own if you want, but it's not something that we're going to worry about. But here is the answers. So it shows you the deviation. Yeah, just pass over it. I'm not going to make you calculate that on a test. Yeah. It's basically having you plot it and figure out that it is what it is. Okay? And then this is proving that the 22.4 liters, yeah. So that brings us to Charles's law. That's what we care about next. Okay? Charles's law, you probably learned it as V1 over T1 is equal to V2 over T2. This is usually a better way to remember it because then you don't have to, it's already cross multiplied for yourself. But volume and temperature, are they directly or indirectly proportional? Directly, right. If I heat them up, speed them up. So if I, that's a different one. If I heat the particles, the volume increases, right? Yeah. Anybody ever leave a bag of chips in your car, and what happens when you come back?
It popped.
Yeah, or it's very, very, because the volume expanded when the temperature increased. Okay, volume and temperature. Let's do a Charles law problem real quick. I'm doing one of each, and if you don't know from there, you're going to have to go back to Khan Academy and learn your gas laws again, because this is very much a review from Chem 1. This is Charles's law.
Do you have to change to Kelvin?
Yes, you have to change that's a very good question. You have to change for Kelvin for every stinking gas law problem there is, right, Zeke?
Right.
Every one you change to Kelvin. There was not temperature involved.
Ooh.
That's not a ooh.
Did I not do that?
Okay, so we are solving for V2. So this is going to look like this, V1 T2 over T1. Okay, so we have 2.58 liters. T2 was 38, so we can either do it right there in the problem, 273, or you can do it ahead of time. And then divided by the T1, which was 15 plus 273. You can either do it in the problem, or you can just do it in your calculator and throw it in there and just put it in Kelvin, and they'll know what you did. That's not something you actually have to show.
Is this the kind of problem that would be like multiple choice, or
This would almost be for sure a multiple choice type
so,
thing.
like, gas laws wouldn't be like free response?
If gas law is going to be a free response, it's going to be kind of like on that last test where it's built into the problem. Like you had to do ideal gas law to get number of moles, or you had to do the dirt over P one to get the molar mass, and then be able to continue forth. So if a multiple choice for sure they'll have a gas law by itself, but in a free response, gas laws are built into other problems. It's never just here's a whole free response over a gas law.
For some reason it changes pressure.
In this case, we don't care because pressure, well, actually, okay, so if pressure is changing, then it's a different problem. Boyle's law holds true if, so Boyle's law was volume and pressure. It holds true if temperature and amount is held constant. Charles's law holds true if pressure and amount is held constant. So the only thing changing in these laws are the ones that we're dealing with, the variables that we're dealing with. That was a very good question. I'm glad you asked that. Yes.
Is this a 2-day test?
Yes.
She put it all in.
Did you say pressure and
It's on the board.
constant?
What?
Pressure and amount or amount?
And. Yeah, and. Okay. So we do that math and we get this answer. Okay? We can also, when we're approaching these, you can also, sometimes on a multiple choice question, you can actually answer it without doing some math, or you can at least throw out some questions or answer choices. For instance, if I'm doing this one, volume and temperature, I am doing what to my temperature? I am increasing my temperature, correct? No.
No.
Yeah, I'm increasing my temperature. So before I ever work the problem, what do I expect my volume to do? Okay, I'm going to ask that again with everybody. I'm trying to give you some tips on your AP multiple choice, and y'all are not listening, okay? I could throw some answer choices out if this was a multiple choice question, in that if in this problem, my temperature increased, so what do I expect my volume to do? Increase. So if I'm looking at answer choices that have a smaller volume, I can immediately throw those out, and now I have less answer choices to choose from on a multiple choice test, okay? So kind of when you're approaching these and you're reading these problems, you should try to approach them in the thing that before I ever do any math, or before I ever even try to answer, am I understanding what's happening in this thing? And so I underline that, and I should say, expect volume to increase. Could be that there's only one answer choice that actually increased the volume. Choose that one and move on, and don't waste the time calculating it, right? If 3 of the volumes decreased and 1 increased, you don't even have to do the math to figure that out, right? Okay? So that is Charles's law. And then here's what's going on a molecular level. The particles, anytime we're drawing, this is something to know too, anytime we're drawing the movement, either with this way, the longer trail, I guess, so to speak, is going to be higher energy or faster movement. Sometimes they'll show it with vector arrows. If they show it with vector arrows, the longer arrows mean more energy. Okay? Okay? That next one is Gay-Lussac's law. And that relates pressure. Again, pressure and temperature. What kind of relationship would you expect? Direct. If I increase the temperature, what happens to the pressure? Think of an aerosol can in the fire. What happens to it? It blows up. Right? You should never do that. It's incredibly dangerous. Okay? And then we have, so if you go back and look at this law, Gay-Lussac's, it works the same way as volume and temperature did. We're just now putting pressure in there. Again, Gay-Lussac's law holds true as long as the volume is being held constant. Avogadro's law is the same concept, except now we're doing volume and number of moles. I do want to write that in. They gave you the proportionality, but they did not give you what the law is. That's Avogadro's law. So number of moles and volume are directly proportional, which makes sense. If I increase my number of moles, I should increase my volume. I'm adding more stuff, right? Yes. And then that brings us to the combined gas law, which is all of those other ones combined. You could throw in there if you wanted to. We don't normally, but you can. And that's combining all the 3 of them. And now we have Avogadro's law. So let's do that one. So we're going to have V1 in 2 equals to V2 in 1. What would be the volume? So we're looking for V2. So that's going to be V1 in 2 over in 1. So plug all that in there. Actually, you could do it this way, or you could do it stoichiometrically as well. I could do, if you want me to show you both ways. Oh, I think I had to figure out how many moles. That's what I did. So what I did here is I had 0.5 moles, right? We have 3 oxygen going to 2 ozone. So if I'm starting out with 0.5 moles, it is a 2 to 3 ratio. And that gave me that's a 0.3, sorry. That makes a difference. So I had to find in 2 by doing that, by using the stoichiometry. Okay? How did I do what math?
Like without a calculator, how do you do that?
I have it done from last year.
No, but
Yeah. She probably multiply it out. It'd just be one divided.
Paige is asking if that was a multiple choice.
Oh, 2/3, basically 2/3 of 50. Yeah.
No, like the 12.3 divided.
What? No, 2/3 of 50 is how much? You're asking me how I would do this math without a calculator. What is 2/3 of 50?
2, 6, 1/3.
I know how to do like the split geometry. How do you do like 12 times 2.3 divided by
Well, now this is not a multiple choice question. If it was multiple choice, they're going to usually give you numbers that multiply and divide out better. Okay? But I would take, what would I do? I would take 1/3 of 12, right? I would take 1/3 of 12 and then divide by half. So, but honestly, when you get a multiple choice with that in there, they give you much easier math than that. Okay? Okay, that's Avogadro's law. Now that brings us to the big gun, Pivnert. Okay? The 3 laws that we use to get Pivnert are Boyle's, Charles, and Avogadro's. Okay? So let's do a Pivnert question. This is going to be our R value right here. You can use 0.0821, which I think is what they give you in your yellow packet. Or do they give you the 206? Yeah. They give you 206 and 21?
There's no way they'd be that nice.
Who has their yellow your packet handy? Just tell me which one they give you. They give you the list of constants. I can't remember if they give you 0.082. Either you can use either one. Okay, 206.
What does that little half infinity sign mean?
Wait, that's a 0.
Oh, equal, like it's telling you it's equal to it. Like it's proportion, it's a proportion.
Wait. What?
It's equal. Is that a tilde? So why don't they just put it in?
I don't know. Y'all are focusing on things that are actually really not to be focused on at the moment.
How do we know if it's an ideal gas equation or like the problem?
That is a good question. That one is a good question. So Michelle wanted to know, how do we know whether we're going to use one of the basic gas laws or the ideal gas law? Okay. Basically, it's this. If they're giving you parameters that are changing, they give you like a parameter of, say, pressure, and they say, I changed the pressure, and now the pressure is this. What is the new volume? That's going to be one of your basic gas laws. If they're just giving you one of each of the parameters and you're missing one of them, then it's going to be an ideal gas law. Okay? Because if you look at ideal gas law, there's pressure only appears once. Volume only appears once. Whereas in like Boyle's law, you've got a P1 and a P2. So if there's a change in a parameter and they want to know how does that affect the other parameter, then that's a basic gas law. If they're just giving you the parameters or they're not changing anything, then it's going to be ideal gas law. Okay? So the only thing that we need to do here is convert temperature, which is easy because it's 0 degrees Celsius. So that becomes 273 K. So we're solving for moles. So it's going to be PV over RT. So 1.5 atmosphere, volume of 8.56, divided by 0.0826.
Whenever we're calculating it, you want us to do 0.0821 or 0.06?
Either one is fine. If they're looking at the problem, I tend to do 0.0821, but you can use either one. They look at that and say, okay, if you're off by like second decimal places because you use 21 and I use 206. Yes, Paige?
For the response, do you have to write all those units for the R value?
You should.
You get the
I don't. When in doubt,
You should always label it.
you should label your
It's
units.
like the first lesson.
Yeah, you should label your units. Okay, and then you cancel, and you get 0.57 moles. Okay? 0.57 moles. Okay? Here we go. I don't think I need to work. Do I need to work another Pib Nerd? We got. Okay. All right, number 11. Which gas law would I use here? Which gas law would you use on exercise 11?
Pressure and temperature.
Well, let's see. Is my pressure changing? Just let's answer this question. Is my pressure changing? Yes. So I know that I need to include some pressure in here, right? Is my temperature changing? Yes. So I need some temperature in here. Is my volume changing? Well, it wants to know what the new volume is, so I need to include volume. So what law would that be? No. Thank you, Mr. Melton, for answering that question correctly. Combined. You would be using the combined gas law because they have 3 parameters that are changing. And so then you would just plug everything in there. What do you need to change?
The number of moles.
The temperature.
You need to change the temperature. Do you need to change the pressure?
No.
Nope, because you don't have R. So you can leave it in. They're both in torr, so you can leave them in torr. But you always have to change temperature. I will let you go back and solve for that because the answer is there. I just wanted to see if you could recognize what law to use. Okay? Surely in exercise 12 you can see to use ideal gas law because it says ideal gas law 2. Say what?
Do you calculate the volume by 22.4?
For which one?
Exercise 12.
No, we are not at standard at STP. You can only do that, which we're fixing to talk about gas stoichiometry. Yeah. Why would you divide by the molar mass to get volume?
And it gives you moles.
It doesn't. Are we on exercise 11?
Oh my god.
Are we talking about 2 different exercises, honey?
Yes.
Oh, which one are you asking about?
I was, never mind. I thought it was like, just kidding.
Okay. I'm so confused, Chance.
I was like, okay, so I saw ideal gas law, and then I saw the 2, I think.
She's talking about exercise 12.
Yeah, and I thought it was 11.
Oh, okay. It's okay. I got you. Okay.
I was like, wait, how do you calculate that?
Okay.
Well, I guess you use a different one.
Yeah, that's just like that's the okay. So here we go. Gas stoichiometry. Use PVRT to solve for the volume of a gas. At STP, we don't need to do that because we already know that answer. What is it? Yeah, but this shows you how you get 22.41. So we'll go ahead and do that. So if I'm going to solve for volume, I'm going to do nRT over P. So 1 mole, and then 0.08206 liters atmosphere, mole K. 0 standard STP, remember, standard temperature and pressure is 0 degrees Celsius or 273 K and 1 atmosphere. And we get that 1 mole is equal to 22.4 liters at STP.
So that's where it comes from.
That's how it gets there. That's where you get that number. Yeah. Okay. So if we are at STP, we do a little happy dance because that means less work for us. And then this next one says a sample of nitrogen. Gas has a volume of 1.75 liters at STP. How many moles are present? So we literally take 1.75 liters, 22.4 liters, mole, and we would get 0.57 0.0781 moles of STP. I could even figure out how much mass of nitrogen gas I have wanted, if I wanted to. What would I multiply by if I was going to do that?
2 times 14.01.
It's Molar mass.
Yeah, 28.02 because it's nitrogen in 2. Okay? Gas stoichiometry 2. This time it says quicklime is produced, blah, 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 yada, yada, yada. But it gives us the mass. So we have to convert that to moles. So we would take that 152 grams, divide by its molar mass of calcium carbonate, which is, I don't have that calculated, 40.08 plus 12.01 plus 16 times 3, 100.09 grams per mole. 152 divided by 100.09 would give me, actually I could just keep going. I could just say 1 mole is 22.4 liters because it's all 1 to 1, right? It is 22.4. Technically, you would need to put that mole ratio in there just to show them that you know what you're doing. So let's put that mole ratio in there. So this was calcium carbonate. And then we would say that 1 mole of calcium carbonate, don't leave out a mole ratio, even if it's one mole of CO2. And then you could say 1 mole is 22.4 liters.
I got 34.01. Maybe I did it wrong.
152 divided by 100.09, and then divided by, 22.4. Well, I did something wrong because I didn't get that answer. Oh, I divided. Sorry, I even wrote it on the top, and then I put it in my calculator divided. I got 34.012. It's probably a typo in the notes. Daniel, I got 01 as well. It's probably a typo. Okay? Okay? Now, what if you are not at STP? Then you don't do a happy dance. You do a frowny dance. Yes, that's it. I agree. It's a frowny dance. Okay? Now, I'm going to tell you that I'm going to have to put a new page up here because I can't fit all the work that needs to be done on the screen. Okay? So, we have two. Well, first of all, let's write the balanced equation.
John, and then they have another kid like, dude, this kid's way better, and they rename their first kid because they don't like it at all. How did you guys remember that? Did they really?
Okay, so here we have our balanced equation. Okay? We have sample of...
Guys, she's trying to teach us the way we do it.
Yeah, you're going to have to work the gas all 3 times for this problem. Would you like me to show you how to do that?
Yes, ma'am.
Okay, thank you. First thing, we're going to have to figure out number of moles of methane, number of moles of oxygen, and then we can work out the problem because we have to figure out limiting, right? Because we have some CO2 that we're forming, but we have methane and oxygen at which to make that happen. So we're going to start with the CH4. And we're going to use the ideal gas law to solve for number of moles. So we're going to do PV over RT. What they gave us was 1.65 atmosphere, a volume of 2.80 liters, and then 0.08206, and then 298. That's going to give us 0.189 moles of CO2. And then I can take that 0.189 moles of CO2. It's a 1-to-1 ratio. Not CO2, CH4, I'm sorry. That will really confuse you. I am so sorry. CH4, 1 mole of CH4 gives me 1 mole of CO2. So that means I can make 1.89 moles of CO2 is how much I can make from the methane. Now I need to do the same thing for oxygen. Let's do that in green. So for I'm doing a limiting reactant for my, because they're both gases, and they're giving me pressure and volume, so I have to figure out how many moles I have. So now I'm going to do the same thing for oxygen, 1.25 atmosphere for oxygen. They gave me 35 liters of that, and that's a different temperature. What is that temperature? 304? 31, yeah, 304. And then I get the number of moles for that is 1.75 moles. And then I do the mole ratio, 2 moles of oxygen, 1 mole CO2, and that means I can make 0.877 moles of CO2. So that's, the methane is my limiting. So now I get to do a third to figure out my volume. Okay, so I'm going to let, is everybody caught up? Because I have to erase to be able to.
Wait, what is that number of the moles of CO2 for oxygen?
Where? What number? There's a lot of numbers up there, sweetheart.
No, like the one where you did N is equal to?
Right here?
Yeah, what is that number?
Oh, it's 0.877.
Oh, okay.
I just was not writing clearly because I knew I wasn't going to use it.
Okay.
Yeah, that's the 877 moles of CO2 from the oxygen, which is clearly more than 0.189, so the methane is my limiting. So now I'm going to take the moles, this moles right here, that I just calculated, and I'm going to plug that into a third ideal gas law, but I'm going to solve for volume now. So I'm going to erase, so don't freak out. So then I'm going to say the volume is equal to nRT over P, because ultimately I'm trying to find the volume of the CO2 that I can form. So I take that 0.189 moles times 0.0821 times the temperature, which is, I forgot. So is that 398? 398 K divided by the pressure of 2.5 atmosphere. And I get my volume to be 2.47 liters. So that is my answer. So that took 3 gas laws. Okay? Any questions on that? Do you understand why we did what we did?
So for the final one, you just use those final values?
Well, we use the gas laws to figure out the limiting reactant, and then we did the mole ratio, just like regular stoichiometry of, whatever, to get to moles of CO2. So if it were like a regular stoichiometry problem and they were asking for mass, we'd take that moles and we would say multiply by the molar mass, but they're wanting volume. So then we throw it into a gas law and solve for volume, since we now know how many moles of CO2 we have. Does that make sense? Okay. I want to do one more problem, and that is the molar mass dirt over P equation, and then we'll stop, because we'll do Dalton's partial pressures tomorrow. So I feel like we should be able to finish off the notes tomorrow, and then Wednesday can be a work day for all. You have a lot of work due when we do Friday. Okay, but that means I'm going to force you to do work. It's not visit time. Okay, because y'all are still a little talkative, especially even after that last test. Okay, so that brings us to density of gases. When we're talking about the density of gases, We're talking about grams per liter because gases are not very dense. So based on that, you can use this equation right here to solve for the molar mass. I've already talked about it being the kitty cat equation, but this is what we want to use. Okay. Of course, if they give you molar mass and they want you to solve for the density, you can rearrange that equation and solve for molar mass as well. So what would it look like? So in this case, we have density of a gas is measured to be 1.95, so we're going to use this. So 1.95 grams per liter, same R value. Uh, 300K. And what was our pressure? 1.5. So 32 grams per mole. That's how that works.
Is this one where you could use further and for liters, just do 1 liter?
You mean like assume a liter?
Yeah, because it gives you the density.
Well, you would well then no. You can't because I don't think you could there.
Wouldn't you use the density to find the number of moles?
Yeah, you would use the density to get to the number of no, because you don't know how much. You can't get to the number of moles because you don't know the molar mass. Yeah, you can't do that.
So